Hello, we have been discussing the semiconductor crystals, and today let us discuss the intrinsic carrier concentration in terms of the band gap. For that, let us consider a parabolic band edges. That means, so this is the valence band edge. This corresponds to EV energy, valence band, top of the valence band, that is the valence band edge, and this is the conduction band, and this energy corresponds to EC, which is the uh, conduction band edge. And the Fermi Dirac distribution function f of E is given by 1 divided by e raised to E minus mu divided by kt plus 1. Here mu is nothing but the Fermi energy, EF. Okay, so this is nothing but this is the probability that an electron is occupied in a given orbital, okay, with the energy E. So if in a given temperature T, some of the electrons from the valence band is excited to the conduction band. Okay, so the probability of a conduction band electron orbital is occupied is given by f of E is equal to 1 divided by, we can write once more this equation, E raised to 1 divided by E raised to energy E minus EF divided by K into T plus 1. Okay, now let us imagine a situation where the energy difference E minus EF is very much greater than KT. Okay, that means this E minus EF, this is of the order of electron volt, few electron volts. But we know that 1 electron volt energy corresponds to, this is of the order of 10 raised to 4 Kelvin. Okay, 1.1 into 10 raised to 4 Kelvin, that is 1 electron volt. So at a normal temperature, that means around 300 Kelvin, 400 Kelvin. So, at that temperature, at the temperature of interest, this become very greater quantity compared to KT. So we can neglect this 1 here. Therefore, f of E become 1 divided by E raised to E minus EF by KT, which is the reciprocal of this quantity. Okay, this first term in the denominator. So that means this become E raised to EF minus E divided by K into T. Okay, T is the equilibrium temperature of the specimen. Okay, so this is the probability of electron orbital in the conduction band is occupied. Now the energy of electron in the conduction band is given by E is equal to EC plus the kinetic energy h cross square k square by 2m. Okay, so this is the energy of the electron in the conduction band. This is the valence band edge and this is the conduction band edge, and an electron in this energy, okay, some energy level E is given by, this is the energy E, and this is the conduction band edge EC. So therefore the total energy here E is equal to EC plus kinetic energy. Okay, and also the density of states with energy E is given by V divided by 2 pi square 2m divided by h cross square whole raised to 3 by 2 E minus EC whole raised to half. So this is the kinetic energy. The kinetic energy is E minus EC whole raised to half. So this expression we have derived in the last class, sorry, the last chapter. The total number of electron orbital is given by 2 into 4 by 3 pi k cube. So this is the volume of k space with radius k, and so this is the total volume into the number of orbitals per unit range of k is given by 1 divided by 2 pi divided by L whole cube. So on simplifying, we get is given by k cube v divided by v is there, L cube is v, so v goes to the numerator, v divided by 3 pi square k cube, and what is k in terms of here, h cross k is h cross k square by h cross square k square by 2m is the energy, kinetic energy. So therefore you can write k square is equal to 2m by h cross square into E is there. So 2m by h cross square E. So k cube is nothing but 2m by h cross square whole raised to 3 divided by 2, or 2me by h cross square whole raised to 3 divided by 2. So here, if we substitute this thing here, the total number of orbitals is given by 2, sorry, v divided by 3 pi square into 2m by h cross square whole raised to 3 by 2 e raised to 3 by 2. Okay, the density of state is given by d of E is equal to dN by dE, which is the derivative of this n. So we get 3 by 2 is that here 3 by 2 e raised to half it will be. So this 3 by 2 and this 1 by 3 get cancelled. So 1 by 3 v by pi square into 2m by h cross square whole raised to 3 by 2 e raised to half it will be. Okay, this 3 get cancelled. We get v by 2 pi square 2m by h cross square whole raised to 3 by 2. Here instead of this e raised to half, this is the kinetic energy here, E minus EC whole raised to half it will be. Okay, so this is the density of states at a given energy E in the conduction band. Okay, therefore the number density of electron in the conduction band is given by, so this is given by the this is denoted by n, small n, so it's equal to, so here the energy, the lowest energy in the conduction band is EC, so this is from EC to, so the upper limit is infinity, can have any energy up to infinity. So EC, integral EC to infinity V d of E into the probability f of E d. So this is the number density. Sorry, this is the total number, and now we have to divide with the volume, then we get a number density. Okay, so this will become EC to infinity, d of E is V by 2 pi square divided by V will be there into 2m by h cross square whole raised to 3 by 2 E minus EC whole raised to half into f of E is f of e, the probability e raised to ef minus e divided by kt, e raised to ef minus e divided by k into t into dE. So this is the number density. So we can take all the constants outside. V and V get cancelled. This will be 1 by 2 pi square 2m. Here we can give this thing m star. Okay, me star we can put. This is the effective mass of electron in the conduction band. Okay, so this is 2me star. Here also this is 2me star, because this is me, because it is the electron mass, and the star represents the effective mass. Okay, so effective electron mass 2me star h cross square whole raised to 3 by 2 integral ec to infinity e minus ec raised to half a raised to ef minus e divided by kt into d. Okay, so for making this equation, this integral into a standard form, we can rearrange this equation. 1 divided by 2 pi square 2me by h cross square whole raised to 3 by 2. So I can take this e raised to ef outside, because this is a constant, e raised to ef by kt. This is e raised to ef by kt. And here e minus ec is there. So I want to make this here also e raised to e minus ec. So this can be written as e raised to minus ec divided by kt. I have multiplied this e raised to e minus ec by kt, then I have to multiply e raised to plus ec by kt also. So therefore I can write integral ec to infinity e minus ec whole raised to 1 by 2 e raised to, so here ef has gone outside, e raised to minus e by kt is there. So e raised to minus e by kt. So and I have to multiply the e raised to ec by kt also. So it will be minus of minus ec by kt into dE. Now let me put this e minus ec as x. Okay, therefore d of e minus ec, which is ec is a constant, therefore this is nothing but dE only, which is equal to dx. Okay, now we have to change the limit also. When e equal to, if e equal to ec, okay, lower limit, then e minus ec is equal to 0, and if e is infinity, then e minus ec also infinity, because ec is finite quantity, small compared to infinity, therefore e minus ec is equal to infinity. So therefore the number density n, this equation over here will become 1 by 2 pi square 2m star by h cross square whole raised to 3 by 2 e raised to e minus, sorry, ef minus ec divided by kt integral, lower limit will become 0, upper limit is infinity, 0 to infinity, e minus ec is x raised to this x raised to half e raised to minus x divided by kt into dx. Okay, this is standard integral. The value is this is, you know, this is gamma of 3 by 2, gamma function, gamma of 3 by 2 divided by 1 by kt whole raised to 3 by 2. Okay, gamma of n divided by a raised to n. Here a is the constant, coefficient a is 1 by kt. Okay, so substituting here, you can write 1 by 2 pi square into 2me, the effective mass of electron, h cross square whole raised to 3 divided by 2 e raised to ef minus ec divided by k into t. This integral result will be gamma of 3 by 2 is 1 by 2 into root pi. This is gamma of 3 by 2 divided by 1 by kt whole raised to 3 by 2. So this will be kt whole raised to 3 divided by 2. Okay, and here pi square is there, here root pi is there, so pi raised to 3 by 2 it will be, so we can take this pi inside. So finally ultimately we get 2 times me star kt by 2 pi h cross square whole raised to 3 by 2 e raised to ef minus ec divided by kt. So this is the concentration of electron in the conduction band. Okay, in the conduction band. This happens only when at a given temperature some of the electrons are excited from the valence band to the conduction band. Okay, if an electron is excited to the conduction band, means there will be a hole left behind in the valence band. The probability of holes in the valence band is given by fh. Okay, this is equal to 1 minus fe. Okay, because electron is excited to the conduction band means there will be a hole, so it is a complementary to this thing. Fh is equal to 1 minus fe, so the total probability is 1. Therefore this can be written as this is equal to e raised to e minus ef by kt plus 1 LCM e raised to e minus ef by kt plus 1 minus 1. So this is equal to e raised to, so divide with this quantity in the numerator and denominator. We'll get 1 divided by, if we divide with this quantity, it will become, first term will become 1, the second term will become e raised to 1 by e raised to e minus ef by kt. So this will be e raised to minus of e minus ef divided by kt. Okay, so this is nothing but we know that we have assumed that this e minus ef minus e is very much greater than kt at a normal temperature. Okay, at the temperature of interest this quantity is large. Okay, the difference in this energy, therefore this can be neglected, this 1 can be neglected, therefore 1 divided by e raised to minus e minus ef by kt is equal to e raised to e minus ef divided by kt. So this is the whole probability. Okay, so the probability of hole present in the valence band is given by e raised to e minus ef by kt. Okay, now the density of states of hole, that is dH of E, is given by V by 2 pi square into 2mH star. This is the effective mass of hole, 2mH by h cross square whole raised to 3 by 2 into so the energy here, the kinetic energy of the holes is given by this is the conduction band, this is the valence band, and this is the valence band edge EV, this is the conduction band edge EC, and this difference is the band gap energy Eg. Okay, here some a hole is present here, given energy E. Okay, so the kinetic energy is given by Ev minus E. So Ev minus E raised to half. Okay, so this is the uh, density of states of hole. Now, therefore, the hole concentration, the number of holes per unit volume is given by. So here, the upper energy of the valence band is Ev, and the lowest limit is minus infinity. So we can write this is from minus infinity to Ev dH of E into Fh Fh of E dE divided by V. So this dH f of E dE gives the total number. Divided by V gives the number total number per unit volume. Okay, so that is the concentration of holes. So here this will be equal to V divided by 2 pi square divided by V is nothing but 1 by 2 pi square 2 mh star by h cross square whole raised to 3 by 2 EV, sorry, integral minus infinity to EV minus E whole raised to half. FH is given by E raised to E minus EF divided by KT into DE. This is given by. So we can do this thing as before to make the integral into a standard form. Can write this thing as and take this e raised to minus ef outside, e raised to minus ef divided by kt. So ev minus e is e raised to half is there. So this also I want to make like that. So this can be written as I will multiply e raised to plus ev by kt integral minus infinity to ev minus e whole raised to half e raised to minus of ev minus e divided by kt into dE. Here also we will substitute e minus, put e minus ev minus e as x. Therefore d of e minus, sorry, ev minus e, d of ev minus e is equal to minus dE equal to dx. So dx is equal to minus dE, or dE is equal to minus dx. So this equation of P will become P is equal to 1 by 2 pi square 2 mh by h cross square whole raised to 3 divided by 2 into e raised to ev minus ef divided by kt. Okay, so here if ev minus e, when e is equal to minus infinity, ev minus e will become ev minus e will become plus infinity, isn't it? If e is infinity, e is equal to e minus infinity, then ev minus e will become plus infinity because minus is there. And if EV minus E is equal to EV, then E is equal to 0. So this will become infinity to 0 into x raised to half e raised to minus x into dE is equal to minus dx. So this will become minus dx. So the minus dx. Okay. So this will become 0 to infinity x raised to half e raised to minus x dx. So this integral also standard form. Here the result is 1 by 2 root pi into kt raised to 3 divided by 2. So this concentration of holes will become 2 times, and simplifying we get 2 times mh star kt divided by 2 pi h cross square whole raised to 3 divided by 2 raised to ev minus ef divided by kt. Okay, so we have obtained the expression for the electron concentration in the conduction band. So that is 2 into me into kt 2 pi h cross square whole raised to 3 by 2 e raised to ef minus ec by kt. Okay, here the whole concentration P is equal to 2 times mh kt by 2 pi h cross square whole raised to 3 by 2 e raised to e. So this is equation number 2. The previous equation, let me put this as equation number 1. So I am writing equation 1 once more here. N is equal to 2 me star kt by 2 pi whole raised to 3 divided by 2 e raised to ef minus ec divided by kt. Okay, so this was the equation number 1. At thermal equilibrium, the creation of electron hole pairs is balanced by the recombination of these electron hole pairs. Okay, so the rate of recombination is proportional to the product of the concentration of electron and the holes. So therefore NP, the quantity which is significant, equal to 4 times MH ME ME star MH star whole raised to 3 by 2 kt by 2 pi h cross square whole cube into e raised to ev minus ef by kt into e raised to ef minus ec by kt. So this will become e raised to minus of ec minus ev divided by kt. So but we know that the difference in conduction band edge minus valence band edge is the band gap. Okay, therefore okay, so this is equation number 3. Equation number 1 and 2, these are the concentration of electron and holes. These are true not only for intrinsic semiconductors, this is true for the impure semiconductor as well. Okay, so for an intrinsic semiconductor in thermal equilibrium, the number of electrons excited to the conduction band is equal to the number of holes created. So therefore for an intrinsic semiconductor, the concentration, so we can write Ni, the concentration of electron of intrinsic semiconductor should be equal to the concentration of holes in the intrinsic semiconductor. So this should be equal to, if they are equal, so we can use this expression Ni Pi square will be Pi square or Ni square. So this will be equal to root of Ni Pi. So this can be written as Ni equal to Pi. Using this expression you can write root of this thing will be this is the expression for intrinsic carrier concentration Ni, which is equal to Pi. So the intrinsic carrier concentration depends on this quantity Eg divided by 2 kT exponentially. Okay. Using the equation 1 and 2, the carrier concentration of intrinsic semiconductor, which will be equal Ni is equal to Pi. Therefore, you can write so on simplifying this, e raised to ef divided by kT is there, minus ef by kT is there, that comes to this side. So we can e raised to 2ef divided by kT is equal to mh star divided by me star whole raised to 3 divided by 2 e raised to here e raised to ev plus ec to be ev plus ec. If we measure the Fermi energy from the valence band edge, okay, so if we measure Fermi energy from this valence band edge, that means the reference ev is equal to 0, and this if this is ec, then this difference is ec minus ev is equal to eg, which is nothing but ec only. Okay, this difference is eg, which is equal to ec minus ev. Ev is 0, then ec is equal to eg. Okay. So ev plus ec is equal to eg divided by kT. So this is the expression for the Fermi energy, which is measured from the top of the valence band edge. Okay. So therefore, this EF, the Fermi energy is given by EF is equal to, we have to take the logarithm on either side. Okay, so Eg divided by 2 plus 3 by 2 kT log mh star divided by E star. Okay, so this is the expression for Fermi energy. Now, if the Hall mass, effective mass of the electron is equal to effective mass of holes, if me star is equal to mh star, then this log 1, it will be log 1 is 0, therefore EF, the Fermi energy, is given by the half of the band gap. Okay, Eg divided by 2. So the Fermi level comes here. So this is EF in the middle of the forbidden region. So Eg divided by 2. EF is equal to Eg divided by 2 if the Hall and electron effective masses are equal. Okay. So this expression is very important. You may get some questions from this. And so we have mainly we have derived this expression of concentration N and P for any semiconductor, and from that we have calculated, we have derived an expression for the intrinsic carrier concentration, which is given by Ni is equal to 2 kT divided by 2 pi h cross square whole raised to 3 divided by 2 e raised to minus Eg divided by 2 kT. So this is also very important expression as far as the exam is concerned. Okay. Now, when we talk about the conductivity of a semiconductor, we have to discuss the mobility also. So you know what is a mobility? It is the magnitude of drift velocity per unit electric field. Okay, that is the mobility mu is given by magnitude of V, okay, divided by the electric field. So this is the definition of the mobility of intrinsic semiconductor. Okay. So if there are, in the case of semiconductor, there are electrons and holes. Okay. So the total conductivity of a semiconductor, intrinsic semiconductor, is given by sigma is equal to, we know sigma is given by Ne mu. For a conductor, sigma is equal to Ne mu, because in conductor the electrons are the charge carriers. But in the case of semiconductor, there are electron as well as holes. So we can write this equation of sigma as Ne mu E, where N is the electron carrier concentration, plus there will be hole contribution also. So P is the concentration of holes, P times E is the charge, and mu H is the hole mobility. Where we can write mu E is given by, mu E is equal to E tau E divided by me star, okay, effective mass of electron, and mu H is given by E tau H divided by effective mass of hole. Okay. So this is the expression of the conductivity sigma is equal to Ne mu E plus Pe mu H. Okay. So this is the total conductivity. Now the conductivity sigma depends on the number density N and P. Okay. As the temperature increases, we know the carrier concentration N is proportional to e raised to minus Eg divided by 2 kBT. Okay. Here, as temperature increases, this quantity Eg by 2 kT decreases, but since this has negative sign, as temperature increases, N increases. So therefore the conductivity increases. Okay. As temperature increases, the conductivity increases, or resistivity increases, the conductivity increases, or resistivity decreases. Okay. Therefore, the semiconductors have a negative temperature coefficient. Okay. So this is about the intrinsic carrier concentration and conductivity. We will continue our discussion on semiconductors in the next class.